Okay, so you may have received notification, but we are now actively recording this session. You may hold questions till the end. I will announce that I'm stop recording maybe 5 minutes before 3. At that point, you can verbally ask questions, you can enter in things in the chat, or you can just pop in while I'm recording if you so desire. So without any further delay, let me grab one of the PDFs that were uploaded here. Um, so let's see, I have some stoichiometry questions up here. So this first question here, this is asking us to determine what's called an empirical formula. So if you remember from early on in the semester, we looked at empirical formulas as far as they are the lowest ratio of each type of atom to one another. Let me see here. Where's my drawing mechanism here? Somewhere. Hold on. There we go, draw. Okay, so we're asked here to determine what's the elemental analysis, or we're given the elemental analysis by mass here. And then we're asked to determine this empirical formula. So if you notice here, all of these percentages add up, let's see, 54, 37, we add up to 100%, right? So we assume that, say we have, 100 grams of sample. What we can do here is we would divide 54 by the molar mass of sodium, since we have 54% sodium, so that's about 23 grams, right? 22.99. And then we would find out a ratio of moles, one to another. So let's see here. So say we divide 54 by 23, we get about 2.35 for our ratio for that, or our amount of moles rather. Then we have boron here. So this was sodium. And we have boron. So we have 8.5%. But if we had a 100-gram sample, we could say we have 8.5 grams. Boron is about 10.8 grams per mole. So we do our 8.5 divided by 10.8, and that gives me like 0.79. All right, so these are not real round numbers, but remember we have to divide by the lowest value of moles to determine our true ratio. So we have left oxygen here. Oxygen, we have 37.5 grams divided by oxygen's what? 16, right? So 16. So we have just over 3 moles there. Let's see. So I'm sorry, just over 2. What am I saying? 37.5 divided by 16. So we have 2.34. All right. So notice the ratios of sodium, or the amount of moles rather of sodium and oxygen are similar here, 2.34, 2.35. We're going to divide all of these by 0.79. So this will tell me that I have 1, right, would be my answer for boron here, because I divide 0.79 by 0.79. And then if I took my 2.35 and I divide it by my 0.79, that'll give me, for both of these, about 2.97. So I'm going to say that there's probably a 3 here, right? Because when I divide this by my 0.79, I get 3, just about. And then I'm going to get the same thing over here. So that's what we've determined here using our imaginary 100-gram sample that relates to this 100%. We find out how many moles we have of each. We divide by the lowest amount of moles, and then we generate this ratio. So that's what I see here. I see sodium 3, and then I see 1 boron, right? And then, oops, and then we have 3 oxygens. All right, that was supposed to be a 3. So we see Na3BO3, and that's how you would determine this empirical formula. All right, so that was way back when, but hopefully you haven't lost that knowledge, because you probably will see at least 1 or 2 questions on the final that deal with that. So I'm just going to keep going until somebody tells me to stop. Let's see here. Another kind of stoichiometry type of problem here. Um, we're to determine the mass percent here of oxygen. Oh, Sorry, my stylus keeps going crazy. So the mass percent of oxygen in this iron sulfate. So this is specifically iron 3, right? We know that because of the charge or the subscript next to the sulfate. So what do we have to do? We have to figure out the total mass of oxygen in our sample and then the molar mass overall of our compound. So let's do that. I might not write out all the numbers for obvious reasons because of my stylus, but let's see here. What do we have? We have 55.85. We have two of those. So that will give us 111.7 for my mass of iron. Plus I have 3 sulfurs, right? Because this subscript gets distributed to my S here. So I'm going to do 3 times 32, 0.06. All right, so now I'm up to 207.82, and then I have, what do I have? 12 oxygen. So 12 times 16. Let's see here. Oops, I'm going to write down what I'm up to so far. Oh, this is with just the iron and my sulfur. Sorry, guys, I don't know what's going on with my stylus here. 207.82. And then we're going to add in all those oxygens, right? So I have 12 times 16. So that's another 192. All right. This is not going as smoothly as I hoped. All right, so we're going to add 192 plus my 207, 207.82. So this will be my molar mass for my iron 3 sulfate. It is just under 400 grams per mole when we add this all together. So what we need to do is just take the amount of oxygen, so that 192, and then divide by our total molar mass. So 192 over about 400 will approximate. And that gives me 0.48. And what we see here, the closest answer to 48% is this 48.01. So you'll be given the periodic table. So all the values that I'm pulling from my periodic table that you can't see, you'll be given those values. So again, all we have to do here is find the mass of oxygen by itself. So that was the 12 oxygen times 16. Divide that into the total molar mass, which was about 400. But you can see with approximation, you can still get the correct answer, even if you're not exact. So 48% will be the mass percent of oxygen in our iron 3 sulfate compound. Let's see, we can do another one or two here. Okay, so I have some notes here. So we have this silicon chip mentioned here, right? And we have a mass of silicon that's in that chip. And if it was pure silicon, how can we determine how many atoms are in that chip? So as I wrote over here, the first step would be to convert to moles. So if we do that, we would have to look up our molar mass of silicon. So that's about 28 grams per mole. So that's what you see down here, this 28 here. So I took my mass in grams, so that 2.34 to the -4th, divide by 28 grams per mole. That gives me how many moles I have, right? So that's this step right here. Oh, it's good. I can just point out what they already have written. And then to go from moles to atoms, remember we need our Avogadro's number here. So 6.02 to the 23rd. So if we look, the closest answer here would be answer choice A, and we would have about 4.9 to the 18th power of atoms. All right, so know how to find molar mass. Don't forget Avogadro's number when that's useful when we do gram to mole conversions. Also know how to put in exponents into the calculator that you plan to use for the exam. I will request some loaner calculators to make sure that everybody has one that's suitable. But one acceptable calculator, something like a TI-30, oh, I can't write it, a TI-30X, something like that, as long as it can't store data, you'll be good to use it. So let's see here. what else do we want to talk about that you might see here? How about mhm. Something like this, problem number 5 here. This uses stoichiometry, of course, because we're in that section. But we might not have seen something like this in a while, maybe like chapter 4 or 5. So let's take a look here. So we want to calculate the mass of this antimony compound here, this fluorinated antimony. So we have 1 gram of Freon. This is our product that we're trying to produce. And Freon is represented over here. So they give you the chemical formula for Freon, this CCl2F2. And we're going to use the balanced equation here to do this calculation. So since it's already written out down here, I'll just kind of point to things as I explain. But we always start with whatever amount we're given. So over here, we see 1 gram of Freon. That's our target. That's our goal. So we're going to kind of work backwards and figure out the mass in grams, right? We're looking for grams again of our this antimony trifluoride thing. So what we do is we first convert to moles, right? Because we can't relate grams to grams directly. We need that mole intermediate. So I'm going to divide my 1 gram of Freon by its molar mass. And look at that. They gave us molar mass over here. So this is one less calculation. So I'm going to divide 1 by 121 to get to moles, right? And now I have this, as I wrote in here, this molar ratio right from our balanced reaction up top. And it's already balanced. Remember, if you don't see any coefficients, double check and make sure you're balanced. But if there's, a 3 and a 2 here, the ACS creators of the exam, they will not give you wrong coefficients. So we'll assume this is balanced. And then I want my moles of Freon here to cancel with my moles that I just found. So I'm going to put that on the bottom. And I'm going to take this 3 coefficient. So I have for every 3 moles of Freon that I need to produce, I need 2 moles of the antimony compound. So that's where the 2 came from on top. So we'll divide by 3, multiply by 2. And now we're into moles of that compound, that SbF3, but I want to be in grams. So last step would be to take the molar mass that was provided, multiply my moles by grams per mole. And if you write this out, right, on your scrap paper, right, if I could, moles will cancel with grams per mole and will be left in a unit of grams. All right. So I'll assume no questions since I don't see, I'm sorry, I can't see the chat, but I don't see any hands or anything. All right. So let's see if there's anything else useful in this section. Titration here. So we looked at acid-base or redox reactions. You can do titrations and with acid-base chemistry. You can also do redox titrations. So it looks like that's what we're looking at here. So we have this balanced reaction here. Remember, we have coefficients, so we'll assume it's balanced. And we're asked to find a volume of a specific concentration of reagent. So we have this 0.1 molar SO3 ion here, the sulfite ion. And we want to know how much of that volume-wise is needed to titrate 2.4 milliliters, or 24, I'm sorry, milliliters of this concentration. So we have a volume here, and then I have a concentration. So what do you think we need to do? We need to get to moles. So what they've done here in the calculation steps is we start with what we're given, right? First, our volume of this iron 3 ion. So we have 24 milliliters. And instead of converting to liters, they multiplied by millimoles. So this is the same thing as if you divided and convert it to liters, you would have 0.02. So what we found here is that they've used a kind of like a shortcut. They've just changed it to millimoles. So we would get the same answer if we divide it by 1,000 and convert it to liters. But since this is the setup that they used, we'll continue with this. And I noticed that my concentration is in moles per liter. But that's where that same concentration can be used. You still use the 0.2 coefficient, right? But we just changed it to this lowercase m here for millimoles. All right, so I'm going to multiply my volume times my concentration. That would tell me how many of these, thousandth of moles that I need, these millimoles that I need. And then I'm going to go back up to my balanced equation to get my ratio here. So I could say to myself, for every 2 millimoles of iron 3, right, we'll cancel that out. I could titrate 1 millimole of my SO3. So that's on the top here. So that's where those coefficients, the 2 and the 1, came from. And now that I'm in millimoles of my ion here, I can go back to my information from the equation, and I'm going to just divide by the concentration in millimoles per milliliters, which would be the same as moles per liter, right? So if we have millimoles per milliliter, we can see that milli, right, translates to the original mole per liter concentration. So we're not really doing anything different. We're just going to end up in milliliters instead of liters at the end. So my last coefficient, I'm going to divide, the millimoles will cancel, and I end up with my volume in milliliters. So nothing's really different than what we've practiced in class. It's just that instead of converting to converting to liters, they kept it in milliliters. All right, so I think, oh, there's some more good stuff here. All right. I was going to say we could switch topics, but let me do this one together as well. So again, this is in the stoichiometry section, question number 7. Let's see here. So for this, we want to know what percent mass of nickel was in an impure sample. So let's sort this out. Let's figure out what information we're given, what we should start with, and let's see how we can do this here. So I have a 17-gram sample, and I'm told that it's impure. It's going to react with carbon monoxide. So that's what we see down here in this given equation. We see my nickel, my impure sample of nickel reacts with carbon monoxide, and we get this nickel carbon monoxide compound here. And we form 6.25 liters of solution, right? So let's see, I'm sorry, of this gas. I'm sorry, not liters of solution, but liters of gas, right? So let's see how we can figure this out. So what are we given? We're given our volume in liters. We're going to start there, right? So I'm going to take this volume in liters. And I'm told that this is at standard pressure and temperature. I'm like, it's in here somewhere, STP conditions. So we have to assume that the volume of a gas at STP will be 22, oh, that should be 22.4 liters. And this we could solve for. So if you don't have this memorized and you want to know the moles of gas at STP, you could just plug in to our PV equals nRT expression. You just solve for moles. I'm sorry, you would solve for volume. What am I saying? You would solve for volume. We would assume 1 mole of gas, and we would say nRT over P. We would plug in 1 atmosphere for pressure, 273 Kelvin times our 0.08206 for R, and we would end up getting 22.4. I think we did this in class together. So that's where this conversion factor came from. So we have our liters. We know the molar volume of any ideal gas would be that 22.4 liters. So I'm going to cancel these out. And now I know how many moles I have of my nickel carbon monoxide compound here. And what I want to get to is the grams of nickel in the end. So this is where I'm working towards. And right now I'm in moles of this nickel compound. So I'm going to use my balanced equation here, which is 1-to-1 molar ratio, to convert to how many moles of nickel I have in this reaction. And then my last step here will be to get back to grams, right? So we have every bit of information we need. We'll go to the periodic table. we'll look for nickel, and that's about 58.7. Yeah, I have 58.69. So we would, in this last step, convert from moles of nickel to grams of nickel by multiplying by the molar mass in grams per mole. And we'll see that we have 16.4 grams of nickel out of our original 17-gram sample. So the last and final step that they're looking for, I apologize, I thought we were just looking for mass, but we're looking for the percentage. So we would divide our 16.4 grams by 17, and we would end up with almost a 96, right? 96.3% of nickel in our original impure sample. So don't forget PV equals nRT. Don't forget if you want to memorize the molar volume of a gas. So for 1 mole of an ideal gas at STP, we'll have 22.4 liters. Let's see here. What else do we want to look at here? All right, I'm gonna stop from this document, and I'm gonna open up. Ooh, hold on. It won't let me minimize. Hold on. Let's see here. Uh, in the background, I'm going to pull up, what do I have next? How about electrochemistry? Because I promised you that I would at least show you the setup for some of these problems that we did not cover in class. But again, just to remind you, that's expected that you don't cover everything in Chem 2. Oh, wrong screen, sorry. So this exam, I should preface, is used for both Gen Chem 1 and 2. So it's used to kind of standardize what's being covered in each of these courses. So again, it's expected that you do not know the Chem 2 material, but I will just quickly show you this setup here in case you want to try. So this is interesting. I like the real world application of the electrochemistry because it covers electroplating here. In question 4, we're asked here, how much time? So we're looking for a unit of time, either seconds or minutes, usually will be our answer, to plate 2.08 grams of copper. And this is that electroplating that I'm referencing. And we're told the current here. So we're given a few bits of information. We're told the current, constant flow here. And one thing that we should note is that this unit ampere is also a coulomb per second. So this right here, this conversion factor that's given down here, an ampere, as I mentioned, is a coulomb per second. So that's where this 1 second per 1.26 coulombs came from. So I understand we didn't talk about coulombs because we did not cover electrochemistry, but just to set this problem up here, I wanted to review that. All right, so let's go back. What were we given? We're given 2.08 grams of copper, and we're given our current. So we want to start with one of those. So I'm going to start here with my mass in grams. I'm going to convert that to moles. As always, right? We need to relate moles to something. So you will probably have to look up a lot of molar masses, or in this case, it's just copper. So we'll plug in 63.5 as our molar mass. We'll convert to moles of copper. And then they give you let's see, the half of the redox reaction that you would use to do this electroplating here. So we have our reduction reaction here where copper ions gain 2 electrons to be converted to solid copper. So when I have my next step here, I see that for every 1 mole of copper, I need 2 moles of electrons. So we haven't looked at this, but this would be the next step in these electroplating type of problems, because I need now moles of electrons to cancel with my Faraday constant. So if you've taken physics at all, you might have heard of this Faraday in general, or Faraday cage. But this is going to be given to you either in your front cover or in the problem as you are calculating it. So that's what we need to cancel out here, right? My moles of electrons with 96,485 coulombs, and it's per 1 mole. So that is assumed here that it's this many coulombs per mole. And now we've moved to this unit here, this C. And next step will be to cancel that out. So that's where our current, our amperes come in. We use that here, and we're going to keep the Coulomb unit with whatever our coefficient is. So for every second that passes, 1.26 coulombs are occurring. Right, so that's where that this next conversion factor comes from. We'll cancel out. So we'll end up dividing by 1.26 here. And now we're in a unit of time in seconds. So at this point, this would not be given to you, but you should know that there are 60 seconds in a minute. If we have to convert to hours, then you would divide again by 60. So 83.6 minutes. If we wanted to get that to hours, we could. All right, so again, I do not expect everyone to get this question right. Most of you probably will not questions like this, but now at least you have some skills that can help you if you want to attempt it. All right, let's see. I think we looked at this one together in class. I think all the sections. So I'm gonna keep moving here. Let's see. How about we have this is again more just electrochemistry, cell potentials. Let's see here. All right, I'm going to go to a different section because I really wanted to just show you guys the electroplating stuff. Since you definitely will see at least one question on that. I'm going to move to the next sections on energetics. So this deals with energy, things like enthalpy, a term that we did not learn yet called entropy, which has to do with the disorder or the chaos of our system. Hold on one second. I can't find it in the background. Let's try again. All right, so energetics. There we go. Maybe if I have to switch to there we go. Okay. All right. So you should be seeing what I'm seeing now. So this question here specifically, number 8 in this section, we'll take a look at. So this is an equation that we did not learn, but I'm going to introduce it here. Oh, whoa, sorry. My pen has increased its width here somehow. All right, well, just deal with it, I guess. Oh, here you go. We're back to normal. So we have this equation here that I just outlined where we're going to relate what's called Gibbs free energy. So this is overall, if we added together the enthalpy term here that we're used to seeing, this delta H, and we incorporate this other term over here, which has to do with that entropy or chaos of our system. We're asked to just determine, using this equation, what we would think these circumstances for free energy changes would be relatively temperature independent. So that means when would it just really depend on the enthalpy of our reaction? So what this is asking us to consider is that if we had a very low temperature, a very low value of either positive or negative entropy, this equation, this value for Gibbs free energy would not be temperature dependent, right? So it would really only depend on whether we have an endothermic or exothermic reaction. So that's how this equation can kind of be interpreted, that we have this total energy of our system, this delta G, and it's a combination of both the bonds breaking and bonds forming, that delta H, that enthalpy value, and then we subtract a temperature-dependent term, this T, and then the change in entropy here. So if you're asked questions about Gibbs free energy or about temperature dependence, it has to do with this delta S, this entropy term. And the word that I'm saying is entropy. All right. So we know enthalpy, we know delta H, but we have not seen much of at all about chaos or disorder of our system. All right. Yeah. So I noted over here, in Chem 1, we do not cover this, but just now you guys have the upper hand. You know how to relate these equations. Let's see here. What do we have? Um, hmm. All right, so something like this, we could do easily, right? Using that delta G equation. So that's what we see down here, right? Oh, if we use our original, delta G is delta H minus T delta S. We can just plug in some numbers. So if we're given an enthalpy change, right? So our delta H is negative 18.4 kilojoules. So that's what you see plugged in there, where the delta H is. And then we're going to subtract our temperature times our delta S. One thing you might have noticed is that there's different units here, kilojoules and joules Kelvin. So our temperature dependent term has Kelvin as a denominator. So that's what we see here. But we can't combine kilojoules and joules together. So we had to convert using 1 kilojoule per joule here. So what happens is this entropy term would then be like negative 0.263 times 298. And we would get 70 from that. So negative 298 times 0.263 gives us 70 kilojoules. That's gonna be positive because our negative and our negative will cancel out. So we're gonna add that positive term to our negative term here. And as long as you know what to plug in where and you know to convert to kilojoules from joules, you have the ability to answer these Gibbs free energy questions correctly. All right, let's look for stuff that we have seen here before. How about some calorimetry stuff here? Um, Okay, I'm looking for stuff that I know we've covered. Um, Solution process. Let's see here. So this is the solution process. This is referring to something dissolving, right? So creating a solution. So we're told that we have this sodium compound here that is a hydrate. So we briefly mentioned hydrates being compounds that have water molecules built in, part of them. And we're told here that when this dissolves in water, our solution gets cold. So if you remember, that means that we would have to put energy in to our process to get something to dissolve. Remember I mentioned that, if you're holding something as it dissolves and the beaker gets hot, that will be exothermic. But if our beaker gets cold, this is telling us that it's an endothermic dissolve process. So energy from the outside is going in to dissolve this. So our beaker, our solution will get cold. So that shows that we're going to have an increase from when our compound is solid. As it dissolves, we have to put energy in. So we're going to see this increase in enthalpy. And then things would level off after the dissolve happens. So this would be showing us like an exothermic process over here where energy would be released in a solution process. And then these are just kind of like silly representations. But now looking at graphs like this, you can interpret a delta H, a change in enthalpy. If it's a positive enthalpy change for a dissolve process, your beaker will be cold, your solution will be cold. But if it's a negative enthalpy change in your dissolve process, that would imply, right, this negative delta H here would imply that it's exothermic and it would get hot. So commonly, if you dissolve acids in water or dilute them, you can have this exothermic type of reaction. All right, let's see. Trying to find some more relevant stuff here. Mm, Lots of enthalpy of combustion. Let's see. Now, you won't have this many problems that deal with this type of calculation. So don't be, shocked if there's not this many calculation questions that deal with enthalpy changes. Let's see here. Oh, so I gave myself a note here to introduce what entropy is. Entropy, again, is sometimes described as like the chaos or the disorder of our system. So the randomness. So if we're asked here about processes that would have the greatest entropy change, so this could be creating disorder or ordering our system. So we're told here that we have constant temperature. So we're not heating up or cooling anything, but we do see some phase changes here. So in A, we have a liquid going to gas. In B, which is the correct answer here, we have a solid going to gas. So if we thought about the order of a solid, how the molecules are arranged, so ice in this case, right, specifically, we would have these nice ordered crystals in our ice. And then when we turn into gas, we know that our molecules are spaced out, they have a high energy, they're moving around. So when we go from solid to gas, that is why that has the greatest entropy change, because we go from really ordered to chaos, right? Disorder. Whereas liquid to gas is not that much of a change. Solid to liquid, still not as great a change. And then liquid to solid, that's becoming more ordered, less chaos, more a negative entropy change, but it's still not as much as a solid going to gas. If we decrease entropy, so we're now making something more ordered. Um, let's see. In which process is entropy decrease? So we want things to become more ordered. So if I dissolve sugar in water, that's chaos, right? My water and my sugar by themselves are more ordered, and then I mix them together. Let's see here, expanding a gas. So we talked about gases, they will expand to fill their container. If the gas was in a smaller volume, it's more ordered, more contained, but then we expand it, more chaos can occur. So that would be an increase in chaos. Evaporating a liquid. So this is implying a phase change from liquid to gas. So again, we're increasing the chaos, the disorder. So the only process here where we go from liquid to solid, we're becoming more ordered, right? The molecules have less energy, they're not moving around as much, they're cold. So D here would be a decrease in entropy. Let's see, what else can I? Well, I guess we could
Excuse me.
comment on 26 since we're on this topic. So when a liquid evaporates, we're going from liquid to gas, right? So this phase change here. Um, we know that there's going to be an enthalpy change, right? So there's going to be an increase in heat overall. So we would say that we have to put energy in, heat in. So we have a positive delta H, right? So a positive increase in enthalpy. Or change in enthalpy, and then our chaos, our disorder, when we go from liquid to gas, would also be positive. We're increasing. Um, and remember that delta symbol, that means a change. So the change is going to be a positive change. That means it's an increase. All right, I'm going to stop talking for 1 second here. Let me stop share for a second and just come back and see if anybody, oh, there's something in the chat. Uh, Let's see. If entropy is going from gas to a solid, will it still be considered a large change? Or since it is negative? Yeah, so whether it's positive or negative, we're just considering like the magnitude of the change, if that makes sense. So it doesn't matter if it's increasing or decreasing in entropy, we're just focusing on the change. So a phase change from solid to liquid, smaller than solid to gas. Vice versa, gas to solid, larger change than gas to liquid. And let me know if that covered that. Let's see. I'm going to go to at least one last section here. What did we do? We did energetics, we did electrochem, stoic. Oh, hold on. Let me pull up one other. You're welcome, Chris. Let's pull up one other topic here. Give me 1 second. We can do at least one more. How about molecular structure and bonding? That's a good one. So that deals with uh, what am I talking about here? So all of our VSEPR stuff, the different molecular geometries. Let's see here. All right, so I don't think we did any of this in class together. So I might spend the rest of the time here in this section just to cover the many aspects of molecular structure and bonding here. So remember, there's three main types of bonding or interactions. We talk about covalent bonding. That's between all nonmetals. We have ionic interactions or ionic bonding. That's between, cation and an anion. So two ions, right, to form a metal and a nonmetal. The metals become cations, remember. Anions are nonmetals. So up in the right-hand corner of the periodic table. What else? And then there's metallic bonding, which is all metals. All right. So if we have question 1 here, which molecule has exactly two unshared, aka lone pairs? So remember, we talked about bonding pairs, we talked about lone pairs. And so lone pairs are not involved in bonding. We want to have two lone pairs. So we know boron is electron deficient or an exception, right, to our octet rule. So boron will never have a lone pair. So let's take a look at what we would come to, what conclusions we would find here. If we did all of these Lewis dot structures, that's what we see here for BF3, OF2, NF3, and our xenon difluoride. So all these Lewis structures that we determine from the valence electron count, right, are represented here in the middle. So boron, again, is one of those exceptions. So it only likes to have 3 bonds at any time. It has 3 valence electrons, but for boron. So this would definitely not have any lone pairs. If we did OF2, we would find that we would have 2 lone pairs on our oxygen. Oh, so, sorry, guys. So, I can't really point to them, but the top here, that one's not involved in bonding, and the bottom pair here. So that's going to be our correct answer. And then we would see through NF3 here that we have 1 unshared pair. And then I think we did this in class, the xenon difluoride. So what would happen is that we have 3 lone pairs, and this would actually take on that linear geometry. So when we have that trigonal pyramidal, bipyramid rather, electron geometry, right? We would get that linear structure, but this has 3 lone pairs. So the end result here is that we would have to do some Lewis structures, right, to determine the correct answer here. All right, let's see, what else do we have? And again, I apologize, I can't see the chat, so I'll pop back in a minute if you're asking questions. Okay, so number 3 here. This will make sense in a second. So we have BCl3, which is planar. So remember our discussion about boron, it only likes 3 bonds and it's happy. If you wanted to confirm that, you would, calculate the formal charge. Here we'll do a quick formal charge on boron here. So we have 3 valence electrons. Oh, maybe not. All right, so we have 3 valence electrons. Okay, all right, I'm not gonna waste everybody's time watching me struggle with the stylus. But boron's formal charge will be 3 valence electrons minus, remember, dots plus lines. So BCl3 has no dots. It would have 3 lines. So we would see that as a formal charge of 0. We could do the same thing with chlorine, but we would get all 0 formal charges. So we know that that would be the correct Lewis structure, just boron and then 3 chlorines kind of bonded to it. If we do the Lewis dot structure here for NCl3, after we did our valence electron count and formed our Lewis structure, we would see that there's going to be some valence electrons on our nitrogen. All right, I'm gonna give up. So our NCl3, we have that lone pair after we do our Lewis structure. So that will be why it's the trigonal pyramidal. And what do we asked here? Nitrogen atom has a lone pair, whereas boron does not. So B would be our correct answer choice here, right? But again, you have to do Lewis structures to confirm that. Um, and here we go. We see some bond angles. So this is good to review. Trigonal planar has the 120-degree bond angle. Trigonal pyramidal. Um, I tell you guys, it's just less than the 109.5. You can see that it's very close to that, 109 here. But again, as long as you know that it's going to be less than tetrahedral 109.5, you'll be fine for the test. Oh, for the final. Let's see here. We know this, right? The geometric structure. So this is saying the molecular geometry. That's another way of saying that. The geometric structure, right? We have O in the middle, two lone pairs, two bonding pairs. So we know 2 and 2 will give us a bent structure, two lone pairs, two bonding pairs on our central atom. Um, and if we wanted to know the bond angle specifically, it's not going to be 180 because that's linear. It's not going to be 90 because that's in our trigonal bipyramids or octahedral. And then we have bent does not have 120. That's our trigonal planar. So that's shown right above. So the only correct answer that makes sense here is that we have two lone pairs, two bonding pairs, and we have less than that 109.5. All right, I'll do maybe a couple more in this section and then I'll come back. Let's see. So we have sulfur dioxide here. Oh, so what do we see? What do we see in sulfur dioxide? I see two bonding pairs here. I see one on that side. Over here, I see one on this side, two on that side. And then the oxygens have switched their numbers of lone pairs as well. So the oxygen on the left over here has two lone pairs, whereas the oxygen on the right here has two lone pairs. So what are these things? These are resonance structures. Um, so grading your most recent exams, a lot of you do know that resonance structures only move electrons, but for those of you that did not, no atoms will move. So let's see here. The two bonds in SO2 are of equal length and the electron distribution is identical. Well, yes, that is a true statement, right? But based on the fact that these are resonance structures, we know that. We know that the bonds are not going to be longer, right? Remember, the resonance structures represent two wrong interpretations, but when we combine them, the average of these bonds is what we really see. So they don't alternate. No, no, no. They don't resonate like we think of sound resonating. So C is wrong because we don't have any alteration or alternation. The molecule revolves. No, so the molecule's not like rotating or revolving. What we see with resonance structures is that we actually have an equal distribution when we experimentally measure SO2. For both the oxygens, they have the same amount of lone pairs, the same amount of electron distribution, as do the bonding pairs. All right. Let's see. So know the trends just in general, what ionization energy is, what electron affinity is. So just know the general trends. Again, you'll be provided with a periodic table. Let's see here. What else do I want to tell you quickly? The different compounds, like an ionic compound, for example, when we dissolve it in water, it will conduct electricity, conduct electrical current. So current is another way of saying electricity. Um, let's see here. They do also generally have high melting points, but the best answer here would be that when we dissolve something in water, we would conduct current. Yeah, yes, ionic compounds are generally soluble in polar compounds, but we want to know experimentally how we could show this. So sometimes some answers you may convince yourself are right some of the time, but make sure you look for questions that are right all the time or answers that are all the time. Okay. The last thing that I'll review here before I come back, this molecule here, why is it nonpolar? Right? Why? Because both sides of the molecule, if we were to divide it this way, are the same. If I was to divide the molecule this way, I see high symmetry. With all these other compounds, right, I have some lone pairs on my oxygen, so I have polarity pointing this way. Again, lone pairs make this polar in this direction. Um, both of these will have, both of these are fairly electronegative. They're both halogens, but we would also see, a difference in the bonding. So any difference in electronegativity, rather refers to a polar bond. So we're looking for nonpolar. So we're looking for something with high symmetry if we see polar bonds. Hybridization while we're here. Remember, if I need three bonding pairs and a lone pair, that means that I need four degenerate orbitals. And if I add together one s and three p, I get four sp3 hybridized orbitals. And that will be able to accommodate ammonia's lone pair. The rest of these, PCl5, we would need some d orbitals. Boron, these would just be sp2 because I only need three bonds. SF6, I'm going to need some d orbitals there as well. I would need sp3d2 for A. All right, so hybridization, let me come back here. All right, so how's everybody holding up? How are any questions for me? Do you guys want me to stop recording and ask some questions? All right, let me do that because I don't know what you guys are thinking. Pause. Okay, I'm going to stop record. So this will be our review session.